Dear colleagues, welcome into this live IFCC webinar hosted by the IFCC Working Group on Metabolomics. My name is Eli Fuchs, and I am chairing the working group and will be moderating today's sessions. We will have 3 presentations today. To start off, I will introduce the working group, the objectives of our working group, and our members. Then, I will introduce the concept of metabolomics for those of you who are not familiar with this field. Then, 2 of our working group experts will focus on 2 very exciting topics. Dr. Arne Bent will focus a talk on clinical lipidomics and share the progress being made by the community in bringing lipidomics assay to the clinical routine. Then, Dr. Jim Otvos, who dedicated most of his career to clinical NMR, will share his experience in translating assays from research to the clinical lab. I will introduce the speakers in more details at the beginning of their talk. Just 1 second, and I'll be sharing. So before we start with the metabolomics introduction, here a few words about myself. I'm a bioanalytical chemist, and I've been working for more than 50 years in mass spec and separation science field. After my PhD in chemistry, I did a postdoc training at the Food and Drug Administration in the US. And in 2011, I joined Metabolomics, a BASF group company, which has pioneered the discipline of industrial metabolomics. I held several R&D leadership roles and supervised targeted and untargeted metabolomics applications. In 2017, I joined the R&D of Roche Diagnostics in the south of Germany, where my team and I support the development and commercialization of IVD products using mass spectrometry. So in December 2021, the IFCC Emerging Technology Committee decided to create a working group dedicated to metabolomics and appointed me as the chairman. By the beginning of 2022, several internationally recognized metabolomics experts were approached and the working group was initiated. And you see them on your screen now. We now have a great global team with a deep expertise in different fields of metabolomics, targeted and untargeted metabolomics, lipidomics, volatolomics, inborn error of metabolism, reference method, clinical toxicology, mass spectrometry, and NMR techniques. This working group is part of the Emerging Technology Division led by Sergio Bernardini. The division has the ambition to facilitate the implementation of new technology from research to clinical labs. And that's how we define our objective within the working groups. So, and one of them is to provide periodic updates on the application of clinical metabolomics, about the technology, about the methods. So we're trying to monitor different applications and even invite occasionally external researcher or entrepreneur to our meetings. We're always very interested to hear about new technologies and assays. Also, we want to provide IFCC members and the healthcare community with educational resources like this webinar today. We are reviewing the current guidelines and globally accepted metabolomics protocols in order to identify areas of agreement, disagreement within the clinical metabolomics community. The long-term goal is to provide recommendation about those guidelines and protocols. Of course, we don't want to do this alone. We want to build a network or join existing network with international and national metabolomics society. We are very open for collaboration and exchange. So if you feel that we can contribute, we can work together for these objectives, please contact us. So now let's jump to the introduction of metabolomics. So, metabolomics is an analytical approach. It's a multi-step, high-throughput process for the simultaneous detection and quantitation or semi-quantitation of a large scale of small molecule that we commonly known as metabolites. So when we talk about clinical chemistry or clinical application, of course, we think about serum, but metabolomics can be applied to other matrices, such as tissue, for example. What you see on the background of the slide is, so each dot that you see on the background represents one metabolite, and each line represents a chemical reaction. So those are the metabolic pathway. A metabolic pathway is a series of connected chemical reactions. And metabolomics is about looking at the full set of those reactions that happen in a cell at a given time. Now, most of you have probably seen these slides. This is where metabolomics fit in the central dogma of molecular biology, showing the flow, the cascade of information from DNA to the phenotypes. So there are different types of omics. Omics, the meaning of omics is that all constituents of a system are considered collectively. We have genomics, transcriptomics, proteomics. And those are all system approaches that allow a better understanding of different interaction in the biological system. And they all answer different questions. So metabolomics is the omics which is the closest to the phenotype. It answers the question to what is actually happening in this biological system and is very sensitive to the environment, such as lifestyle, age, and so on. So there are two main challenges associated with metabolomics analysis. The lipophilicity range. So metabolomics workflows cover metabolites with a molecular mass ranging from 50 to 1200 Daltons or 1500 Dalton, depending on the definition. So when we want to look at metabolite in serum, we have all those different metabolites have very diverse chemical structure and very different lipophilicity. And you can see this on the scale where we have metabolites such as nucleotides or sugars that are very polar with a log P of -10. And at the same time, if you want to do comprehensive metabolomics, you would want to target ideally lipids, such as glycerolipids, which are completely on the other end of the lipophilicity scale. So as you can imagine, this is a huge challenge in terms of techniques we can use, but also in terms of sample preparation. The second challenge that we see is the concentration range. So the concentration range of metabolite in serum is believed to range from 9 to 12 orders of magnitude, which is from millimolar to femtomolar. So this picture with the balloon is actually a picture from the national park in Gorum in Turkey. And I just would like to say, in light of the recent events in Turkey, I'd like to say our thoughts are with the people and colleagues on the ground in Turkey who are struggling with the effect of the earthquake. So the point of this picture is actually to make the analogy between the concentration range from 9 to 12 orders of magnitude to the size range. So it means that what we're trying to achieve with metabolomics will be the same as trying to take a picture from one of those balloons with the same resolution for those big rocks, those that are 40 meters high, and same bacteria. If you get the same resolution in one picture, that would be also capturing 9 to 12 orders of magnitude. So because of this complexity, there's no single technique that can cover this broad range of chemical diversity. And therefore, if you want to have a good coverage, a comprehensive coverage, you would use complementary methods to improve that coverage. But what is a good coverage in metabolomics? So what is a good number? The exact number of metabolites in serum is still unknown. There are some groups that made some theoretical calculation, and they came up to a number of more than 1,000. If you consider all endogenous compounds, exogenous compounds such as drugs and the metabolite, theoretical lipids, as well as food metabolites. So this complexity led to the subclassification of metabolomics. One very known field from metabolomics is lipidomics, which Anne will talk about. And even within the lipidomics, there are methods that are broken down for different types of lipids, such as icosanoids, such as steroids. Another field of metabolomics, which is also to interest to a working group, is volatolomics, targeting volatile compounds. As far as the working group is concerned, we can distinguish between three different methodological approaches for metabolomics. The first one is metabolite fingerprinting, and this is aiming at the classification of sample based on pattern recognition. Here, no identification is necessary, and this is by no means a quantitative method. The second approach is targeted metabolomics. So targeted metabolomics focus on a subset of non-metabolites. The data processing is relatively simple. It uses reference standards. We're looking at absolute quantification and proper identification. Finally, untargeted metabolomics, which is clearly the most complex of the methodological approach, is a holistic and comprehensive analysis of the sample. It includes unknowns and involves complex data processing. It also involves the comparison of features with in-house libraries or databases. And here we're talking about, in general, about the relative quantification. I will now go into more details about untargeted metabolomics. And first of all, I'd like to go over the techniques that I used to do untargeted metabolomics. This is not comprehensive, but those are the three most used technologies. The first one is nuclear magnetic resonance, NMR, and Jim will talk more about this in his presentation. And NMR has the advantage of being, it's quite a stable and robust technique. It's non-destructive, and it's quantitative without requiring standards or calibrators. There's minimal sample preparation involved in NMR analysis, and generally there's no separation needed, such as chromatography. However, out of those three techniques, it's probably the least sensitive one, and those research instruments, like we see on the picture, come with a relatively large footprint in the lab. Another widely used technique is gas chromatography coupled to mass spectrometry. Here, the advantages are, for example, the chromatographic resolution. It's actually quite a robust technique, and the libraries for peak identification or metabolite identification are well established. However, it requires a relatively long analysis time. GC is actually a technique that can be used for volatile compounds. So in case the metabolites of interest are non-volatile, you would require a derivatization step, and you might get into trouble with thermolabile compounds. Finally, probably the most used technique to do non-targeted metabolomics is liquid chromatography coupled to mass spectrometry, and in general, high-resolution mass spectrometry. LCMS has the advantage of being sensitive and has quite a broad chemical coverage compared to the other techniques. It also has quite a high specificity, especially when you combine it with MSMS acquisition. Also there, we have some drawbacks. The robustness of LCMS is often mentioned here, and you have to account for matrix effects and to correct for those. Now, I would like to show what an untargeted screening workflow or an untargeted metabolomics workflow using LCMS would look like. So this workflow will start with the sample collection, and ideally you would use standard procedure to do this sample collection. What you want to avoid here is to generate variability in your sample at this stage already. The second step is the sample preparation. So in metabolomics workflow, we're interested to see as much as possible, so there's usually no cleanup. And for serum, that will consist of protein precipitation. If possible, it is recommended to use automation to do the sample preparation, as again you will reduce your technical variability. Then comes the chromatography steps, where you and this is about separating the molecule in the liquid phase before going to the mass spectrometer in order to make the interpretation of the mass spectra easier. Mass spectrometry, as I said, is used as a detector. There are different acquisition modes you can use with high resolution. You can use the full scan, so just having mass spectrometry in one dimension, or you can use MSMS, which is usually done when you need to annotate your compound, when you need to identify the features you are measuring in your sample. And there are two, again, different acquisition possibilities. Data-dependent acquisition, where you will generate MSMS spectra based on the abundance of your compounds in the MS dimension, or data-independent acquisition, which is going to generate MSMS information on all the features you detected in your mass spectrometer. Different vendors have different ways of using data-independent acquisition. Then comes the step of data processing. Since we are generating an immense amount of information and of peaks, this is an automated process, so where you will actually integrate the peaks, but the data processing is more than this. You will also try to correct for differences between samples, such as retention time differences, or to correct for mass calibration that may have deviated from one sample to another. And after this step comes the statistics, which is not going to be covered here. Then comes the step of identification. And as I said earlier on, identification can be done based on in-house library. This is usually preferred, but it's of course time-consuming to create those libraries. Or you can also do database searches in open sources databases in order to attempt the identification of your compounds. And finally comes the biological interpretation. So you can really go into the pathway analysis and use the annotated feature to do your biological interpretation. So before concluding, I'd like to finish off on this slide. So although the large majority of metabolomics applications are in the stage of early research, the working group has identified some applications where metabolomics-based assays are used as routine assay or are likely to play a role in clinical routine in the future. The first one on the top of the list is a targeted LC-MS assay for cardiovascular disease called CERT1 or CERT2. And this assay is used in the US in some clinical labs and in Finland. And Anne will talk more about this in her presentation. The second targeted assay using NMR is the NMR lipoprofile, who was actually developed by Jim and his team, also in the area of cardiovascular disease. And he will also talk about this assay in more details in his presentation. Another interesting assay that we've identified is the DBI EPI breath from the startup Deep Breath Intelligence. This is a volatolomics assay with a high-resolution mass spectrometry readout to measure valproic acid, as well as to estimate the potential adverse effects of the drug. Another volatolomics-based assay which is commercially available is specific reveal, which relies on chemical sensor to measure antimicrobial resistance. Besides this application, ambient ionization high-resolution mass spec is also worth mentioning. Several research groups are working on this technology with different approaches. The goal here is the classification of tissue in real time. The technique is developed for operating theater in the field of oncology. And finally, I would like to mention that metabolomics has a great potential in the area of inborn error of metabolism, as it has the potential to screen for a higher number of metabolomic diseases. So to conclude, what can we expect from clinical metabolomics? So I touched on my biomarker discovery. You'll hear more about this in a minute. Improved point of care with real-time measurement. Something I haven't mentioned, but that is definitely worth mentioning, is the potential of developing precision medicine, companion diagnostic for patient stratification, and as I mentioned, inborn of errors. But there are also some challenges, and although there's been a lot of initiative in the area of standardization, guideline, and quality assurance, there's still some work to do. So we do have the minimal requirement for reporting metabolomics results, for example, which was a great help. And also recently, we heard about the establishment of a quality assurance and quality control consortium for research labs. And those are great initiatives. Now, the translation of metabolomics technique in clinical routine will require more efforts in this area. Another challenge is the limited amount of reference material we have available, the data size and complexity, especially when you do untargeted metabolomics. And finally, more like an MS problem, so the mass spectrometry peak identification, as most of the feature generating in a LCMS and targeted assay would remain unknowns. So with this, I would like to thank you for your attention and would like to present the second speaker, Anne. So Dr. Anne Bent is Principal Investigator and Deputy Director at SLING, the Singapore Lipidomics Incubator, an internationally renowned R&D program in lipid research and technology development anchored at the National University of Singapore. She focuses on the translation of mass spectrometry-based technologies into clinical application, primarily for lipids and small molecules. Anne is further passionate about training and education and has made substantial contribution to SLING's various workshops and IC lipid training courses. Internationally, Anne is co-instructor of Lipidomics 101, a short course for clinical lipidomics. With clinical translation close to her heart, Anne serves on the Metabolomics Working Group within the IFCC. She further serves on the Steering Committee of Clinical Lipidomics within the International Lipidomics Society and as Associate Editor for the Journal of Mass Spectrometry and Advances in the Clinical Lab. Early 2019, Anne co-founded the global initiative Females in Mass Spectrometry, FEMS, serving as chair on the board. Anne, the stage is yours.
Thank you for the introduction, Ali, and thank you to IFCC for giving our working group this opportunity to highlight the potential of metabolomics. I will focus on a sub-area of metabolomics, which is lipidomics, and talk about clinical applications. I will focus on the relevance and status quo of clinical lipidomics, then highlight one example of clinical translation, and we'll finish with an overview of current barriers to a wider adoption of mass spectrometry-based lipid diagnostics. Of course, lipids are already an essential part of diagnostics, but this is not lipidomics if we use the definition of measuring the entirety of all lipids, but instead, current lipid-based diagnostics use either individual lipids, such as cholesterol, or small multi-marker panels of lipids, such as bile acids or acid content. The most prominent lipid, of course, for diagnostics is cholesterol, And here you see the structure of cholesterol. What most people don't know is that the majority of cholesterol in human plasma exists as cholesterol esters. So I'd like to use this as an opportunity to briefly mention a lipid nomenclature. So here you see the structure of cholesterol, and attached to it is this fatty acid, rendering this a cholesterol ester. And the name of this fatty acid is 16-0, so it means that this zigzag line here, if you count that, you count 16 carbon atoms, and the 0 means there's no double bond. Whereas this other cholesterol ester here, called 18-2, linoleic acid, you have 18 carbon atoms here, and you have 2 double bonds. And in human plasma, we measure in our lab about 36 different molecular species that all differ by the fatty acid. So mass spectrometry is also already widely used for diagnostics. For a full overview, I'd like to point to this book chapter we recently wrote in Lipidomics in Clinical Diagnostics. This book is coming out next month. But yeah, as mentioned before, for lipid-based diagnostics, currently this is not broad lipidomics panels, but instead panels of select lipids such as the secondary hormones, where really the specificity of mass spectrometry is necessary to differentiate between these structurally very similar steroid hormones. Also, it has quite application in newborn screening, especially in rare diseases and inborn errors of metabolism. For example, it's used to differentiate between the different single doses. And then, of course, the cash cow of vitamin D metabolites and the reactors. So here you see how current clinical chemistry diagnostics of plasma lipids look like. You see the different lipids here with their concentrations and reference intervals in human plasma, from the lowly abundant picomolar hormones to the bulk lipids such as triglycerides, free fatty acids, and total cholesterol in millimolar concentrations. So how now a lipidomic assay of human plasma look like? And that's shown here, where you see all the different lipid classes that exist in human plasma, and each line here represents one individual molecular species. For example, as we've seen just now for the cholesterol esters, this line here, for example, represents the cholesterol ester with a linoleic acid. And then every other line here is a different cholesterol ester. And that means that whereas in traditional clinical chemistry right now, it's total cholesterol that's measured, just the cholesterol plus all the sum of all the cholesterol esters. With the mass spectrometry instead, we can measure with a lot more detail due to the mass spectrometry's sensitivity and specificity. So, as I mentioned before, lipidomic readouts such as this one are not routine yet in clinical labs. There might never be, but they are currently anchored in research labs, and in some commercial entities. Some companies also offer lipidomic-based analysis. And over the past 2 decades, lipidomics has been used in thousands of biomedical research studies, trying to understand the plasma lipid concentrations associated with various health and disease states, often aiming to find lipid biomarkers for improved diagnostics. And indeed, for many of these lipid metabolites, a clinical use has meanwhile been suggested, for example, for the triglycerides, for bile acids, for different phospholipids, for the oxylipins, and of course for the ceramides. And I would now like to use the next few minutes to talk about ceramides as an example, how plasma lipidomics has been used to translate research findings into a diagnostic application. And I like to argue why some people think that ceramide tests might have a space in routine clinical chemistry. Where do we stand currently with clinical lipidomics? We are at a proof of concept stage of the technical feasibility. We have multiple mass spec-based methods available that have been validated for research applications, and we have demonstrated that their sensitivity and specificity is suitable for human plasma lipids. Lots and lots of human population cohort studies have been published in the research field for a variety of diseases, such as metabolic diseases, multiple cancer, malignancies, neurodegenerative diseases, such as Alzheimer's disease, Parkinson, non-alcoholic fatty liver disease, and various inflammatory stages, and so on. And indeed, this has led to a vastly improved understanding of disease pathologies, and also lots of biomarkers have been suggested. But as we all know, the translation of these suggested biomarkers into real diagnostic applications hasn't been very successful. There is perhaps this one example of the ceramides in cardiovascular disease that is emerging. So cardiovascular disease, why? As we all know, cardiovascular disease is still killer number one, especially in the Western world, leading to huge cost implications for the healthcare system. And we have a traditional, traditional risk management that is based on cholesterol, and that is good. It's probably saved millions of lives, but it's still not sufficient. And we also have drugs, the statins, and they do reduce the heart disease burden, but they don't prevent all metabolic pathologies, and they also seem to increase the risk of diabetes. So worldwide, lots of cardiovascular disease cohort studies have been performed with the aim to discover better disease biomarkers and also novel drug targets. So close to 10 years ago, Ceramide started to emerge as a new biomarker for heart attack. It started as a discovery work using untargeted lipidomics, measuring about 700 plasma lipids in heart attack cohorts. And the lipids that appeared to be the strongest predictor for heart attack turned out to be the ceramides. And then in the second step, the team narrowed down these ceramides to 4 distinct ceramide molecular species and validated the discriminatory power of these 4 ceramides in additional studies, larger epidemiological studies. So what are ceramides? Ceramides exist in the human plasma. They circulate in blood via lipoproteins. They are bioactive lipids, which means that in addition to their structural function, they act as signaling molecules, for example, leading to programmed cell death apoptosis. In the human plasma, dozens of ceramide molecular species exist, and intriguingly enough, some are toxic and others are benign, which means it seems important to not only measure the total sum of all ceramide species, but instead use the specificity of mass spectrometry to measure the individual molecular species. I'd now like to show you the structures of those individual molecular species, but if you don't want to look at structures, you can instead admire the picture of the Sphinx, this mythical creature, because ceramides are actually part of the sphingolipid family that was named after the Sphinx, as they are the most enigmatic lipids. A ceramide is different from typical lipids as they don't have a glycerol backbone, but instead a so-called sphingolipid long-chain base, which you see here, which has 18 carbon atoms and this one double bond here. So this 18-1, as you see, is present in all these 4 different molecular species. And then attached via this amide bond here, you have different fatty acids. So for the 16-0, 16-0, and for the 18-0, it's 18 carbon atoms and so on. And the toxic ones appear to be the 16-0, 18-0, 24-1, and the benign, if not even beneficial, is the 24-0. And all of these can be easily, well, relatively easily measured and quantified by mass spectrometry. And this then led to commercialization of this assay just 2 years after it was published. The Mayo Clinic licensed this test in 2016, and it's described as a risk marker for heart attack in patients who don't respond to treatment and to young patients with premature CAD, coronary artery disease. Find more information on the website. This test has now been termed CERT1 for coronary event risk test. The reference values are indicated here. As you see, the concentrations are so low that you really need mass spectrometry to accurately quantitate these. To make the interpretation of the measurements easier, they use the ratio of the 3 toxic species to the one that is benign, and then calculate a risk score on a scale of 1 to 12. This first step of commercialization then led to a massive increase in interest in ceramides, and more researchers worldwide started measuring them and other similar lipids in various cohort studies, and that then led to further improvement of the ceramide test. In 2020, actually, the same team added 3 phospholipid species, phosphatidylcholines, and validated this new test, which is now termed SEARCH2, for its power to predict cardiovascular disease risk, especially for secondary events and mortality. And the hope, of course, is that this SEARCH2 test can now lead to an even better risk stratification and identify those patients who are at especially high risk for cardiovascular events, especially death, so that they can receive more aggressive treatment. Yeah, and then also this test was commercialized. Quest Diagnostics licensed it in 2021. So now in the US, 2 companies, commercial labs, are offering this test, and also in Finland, multiple clinical labs are offering this test. And of course, worldwide, in various research labs, lipidomics researchers are studying ceramides in various disease cohorts. By now, there's indeed mounting evidence that the ceramide score performs well in various populations, as it's shown here in this figure, where it's compared with the conventional diagnostics based on age, gender, smoking, blood pressure, total cholesterol. And this conventional diagnostics is not really that good in picking up patients that are at low. It's not really good in differentiating patients that are at low or moderate or high or even very high risk. Whereas the ceramide score SEARCH2 here in the red line is better in assigning those individuals that are at very high risk. And if you combine the conventional diagnostics in black together with the SEARCH2 score into this combination score, then this outperforms conventional diagnostics significantly, especially for death. And this has now also been confirmed in meta-analysis of close to 30,000 patients, and importantly in diverse populations, so in early onset of disease, and the elderly, and people with various comorbidities, and so on. So yes, perhaps indeed the ceramide risk score might now claim its space in clinical chemistry, as it's nicely summarized here in a recent editorial by authors from the Mayo Clinic. How does the ceramide test actually work? You just need 10 microliter of plasma at extraction solvent that would include the deuterated internal standards for the individual species. You aspirate 3 times to mix it and centrifuge, and then the supernatant is used for liquid chromatography, tandem mass spectrometry, runs roughly 5 minutes. You also have to run calibration curves to then determine the concentrations of the individual molecular species. And then these concentrations are used to calculate the ratio and to assign a score on a 1 to 12. From low risk to moderate to increase to high risk. And then this score is used to determine an individual's risk category. So now, what are the advantages and barriers of this lab-developed test for wider clinical adoption? I guess a good thing is that just 10 microliters of plasma is necessary, and plasma is readily available in routine clinical labs anyway. Luckily, the ceramides have been shown to be very stable at room temperature, which is, by the way, not the case for many other lipid species that are out there. So it's definitely a plus. Also, the sample preparation is relatively straightforward and can be automated with robotic systems, for example, in 96 well plates. And the internal standards, the deuterated internal standard mixture for each ceramide species is already commercially available by Avanti Lipids. I wrote it here as a plus that it's sort of semi-automatic peak integration and calculation of concentrations. It's not really a plus. I mean, it's neither a plus nor a minus, I suppose. All of this is still mass spectrometry, which has its inherent problems of being not just pressing the green button and it runs automatically, and mass spec has just its inherent difficulties, being not very robust and not very easy to use, but it is more and more becoming more and more accessible, both in terms of getting slightly easier to operate, and also more and more more and more clinical labs now introduce triple quads into their routine diagnostics. I guess as the biggest barrier to a wider adoption, we have to acknowledge that so far the performance of the ceramide assays have only been shown in observational cohort studies. But what my clinician friends are telling me, what's really missing is intervention studies using the ceramide score for risk management and compare treatment outcome results after 10 years. So, for example, the statin dosage, depending on either the new ceramide score or the traditional conventional risk management. Also, the reference intervals and data on biological variation in diverse populations are not really widely available yet. And also, the ceramide score is obviously not yet part of the existing guidelines, and the actionability of measuring ceramide is also not entirely clear yet, because there are, for example, no specific therapeutic interventions specifically targeting ceramide concentrations. And from an analytical point of view, we need to ensure accuracy across time and space, as with other clinical tests, be they mass spec based or not. Harmonization, if not standardization of the tests, would help with ensuring quality. And proficiency testing schemes or external quality assessment schemes also do not exist yet. Some people argue that all of this will only be possible if the IVD industry steps in. So, in short, it's not the most complicated assay, but it's also not plug and play yet. This brings us to a summary and outlook. So I hope I have convinced you that mass spectrometry is suitable for plasma lipidomics, both in terms of sensitivity and specificity, and that it works well with small volumes of plasma. The current applications are primarily anchored in research labs. Over the past decades, applications of lipidomics has led to an an advanced understanding of the diverse roles of lipid metabolites in a variety of diseases, and has resulted in a number of proposed biomarkers. The clinical translation of these research findings has been slow, but it looks like ceramide testing is emerging as a potential success story from research to a lab-developed test. The biggest concern for lipidomics might be how to ensure quality across time and space. It is clear that if we move from analyzing single lipids to small multi-marker panels to large lipidomics readouts, this really comes with increasing complexity and quality assurance and quality control challenges. We have a lack of reference intervals, of reference materials, and of QA/PT schemes. And it really takes a village to bring this forward. I'd like to highlight a community-led effort that is happening right now, which is the Lipidome Panel Interlab study organized by the International Lipidomics Society's Clinical Lipidomics Interest Group. It's where we're trying to establish the plasma concentrations of about 160 different plasma lipids. And if you'd like to know more about it, please get in touch with me. In terms of translation and commercialization of lipidomics, more and more companies are now offering this as a service for research use only, which shows the growing awareness of the potential utility of lipidomics. And also licensing of defined lipidomic panels as applications for disease diagnostics in areas such as certain malignancies, pancreatic cancer, non-alcoholic fatty liver disease, Alzheimer's disease, and cardiometabolic diseases is happening right now. If you are interested in reading maybe critical evaluation of the potential role of omics in diagnostics, you could have a look at this opinion paper by one of the pioneers of clinical mass spectrometry in Germany, Professor Dr. Michael Burgeser. And with this, I'd like to thank you for your interest, and I am looking forward to our discussion.
Thank you, Anne, for this great presentation. We can already get questions through the chat, and we'll answer them at the end of the webinar. So for now, I'd like to introduce our next speaker, James Otvos. Jim? All right. Hi. So, Dr. Otvos received a PhD in comparative biochemistry from the University of California, Berkeley, and a postdoctoral training in molecular biophysics at Yale University. He spent the following 20 years in academia, first on the chemistry faculty of the University of Wisconsin-Milwaukee, and then as professor of biochemistry at North Carolina State University, during which time he developed new technology for measuring lipoprotein particles using nuclear magnetic resonance spectroscopy. He then founded Liposcience, a company devoted to clinical translation of NMR diagnostic testing, and served on the board of directors and as chief scientific officer, overseeing analytical development and clinical research. Following LabCorp's acquisition of Liposcience in 2014, Dr. Otvos continued to oversee collaborative research to develop novel NMR metabolomic assay addressing mainly cardiovascular, diabetes, inflammatory, and mortality risk. He retired from LabCorp in 2022. Dr. Otvos maintains academic affiliations with the University of North Carolina at Chapel Hill and the National Heart, Lung, and Blood Institute of the NIH. He has co-authors over 250 scientific publications. He is a named inventor on over 40 patents and has received several research awards from the American Association of Clinical Chemistry, as well as the Christopher Columbus Foundation Discover Magazine Award for Technological Innovation. So, Jim, we're looking forward to your presentation.
Okay, very good. Thanks for the introduction, Ellie. I'm going to plunge right in. We've heard a lot about mass spec today, and the advantages of NMR have been mentioned, and they are substantial in terms of the ease of measurement and the efficiency. So that's the good news. NMR is the best modality for clinical translation of metabolomics, so long as the metabolites are present at high enough concentration, namely roughly greater than 10 micromolar. The bad news, of course, is that almost all of the metabolome consists of metabolites of lower concentration, so that's in the realm of mass spec. So really what I want to talk about today is the good news, what one can glean from an NMR spectrum of blood plasma. The NMR spectrum itself can be considered to be untargeted because you get the whole spectrum whether you want to use it all or not. What is challenging, or certainly more challenging, is the quantification of individual metabolites that give rise to observable NMR signals in the spectrum. And that challenge is due to the high degree of overlap with other signals. But it is possible to get a lot of information from a very short, less than 1 minute, so-called blood scan. These are some of the metabolites that can be extracted that I'll talk about a little bit. And then in the brief time I have available, I'll just mention some primary clinical applications that I think really should drive the introduction of NMR into routine clinical testing. So the road to from then to now, it really extends back to 1986, so more than 35 years ago. I'm sure some of you weren't born then, but that's when I first got interested in this from an academic standpoint. And then this became clinically translated by a company called Liposcience and subsequently LabCorp. But what I say at the top is that broad clinical translation is still a work in progress because you probably don't have NMR analyzers in your own laboratory, and that's really what still remains to be accomplished. So I'm going to walk you through quickly each of these 4 phases in the history of then to now. So it began with a paper in the New England Journal of Medicine in 1986 saying that you could diagnose cancer in a very simple way by looking at a proton NMR spectrum of blood plasma. And that created a tremendous amount of interest in the NMR community, including myself. But unfortunately, many other people could not reproduce the phenomenology. So a paper published 4 years later in the New England Journal basically put an end to the idea that NMR could serve this purpose. But in the meantime, it caused us and others to look more closely at what was the underlying phenomenology. And it turned out that the signal that was the so-called cancer diagnostic was a signal from the lipoproteins in blood. And so in the early 90s, we published a couple papers showing that the NMR signal from the lipids in smaller lipoprotein particles versus larger showed up further to the right for the smaller particles, further to the left in the larger particles. And this made it possible to take a plasma spectrum, which is the mixture, and with an understanding of what the underlying signals look like from the contributing lipoproteins, one could quantify LDL, HDL, VLDL, and its subspecies. And so that was patented in 1990 at the very beginning of this trail. So what the process is of taking the NMR spectrum and converting it to quantitative information is dealing with this spectral overlap, which is severe in the case of the lipoprotein subspecies, as you can see here. And so this is, we use a deconvolution approach. In this particular picture, you also see signals from branched-chain amino acids. So these are all quantified simultaneously. And this has all been well worked out and has led to the ability to report concentrations of many lipoprotein subclasses, as well as small molecule metabolites and some multi-markers as listed here. I don't expect you to read any of these things, but all of these things that are reported and able to be reported from a single NMR scan are well analytically and clinically validated. Just one quick example of the need for deconvolution is this so-called glyc-A signal, which is an inflammation marker that I'll talk about a little bit later. And you can see here on the left that this fairly sharp signal shows up on the left side of a broad shoulder that comes from lipoprotein subspecies. And you can see by these four spectra of four different people with different triglyceride levels that the overlapping signal looks very, very different depending on the individual. And this really needs to be dealt with by a complex deconvolution model that makes sure that glyc-A does not include in its quantification lipoprotein information or protein information. So I mention this just because some other folks are reporting glyc-A by NMR whose concentrations are about 3 times larger than the ones we report. And that's because they simply integrate the entire signal and don't really worry about the overlap of the lipoprotein signals. So back to sort of the second phase of this process of commercialization or translation of NMR diagnostic testing. So this was conducted by a company called Liposcience that was established for this purpose. And what it was a lab testing business for its first several years, and then it transitioned into an IVD business with the motivation to make the NMR analyzers available to any laboratory, and that was successful to an extent. But then the company was acquired by a lab company, a lab testing company, LabCorp, and so the IVD business was sort of discontinued. So I'm going to walk through some of these sort of 3 phases of the Liposcience history very quickly. So this is what the NMR lipoprofile test looked like, a 2-page color report that was used for patient care. I'm not going to go into any of the details, but LDL particle number was the main value proposition, but also HDL particles and then insulin resistance index that I'll talk about later. So the practical challenge in trying to start a company devoted to NMR testing was that NMR spectrometers generally look like this. They don't look anything like a clinical analyzer. They have a big footprint. They're not really optimized for efficiently conducting one experiment. They're engineered to be multifunctional. And so what had to be done was to modify research NMR spectrometers into the first NMR clinical analyzers. And so here you see a room at Liposcience with about 15 of these modified Bruker 400 megahertz NMR spectrometers with these Gilson liquid handling systems sitting on top to flow the samples one at a time into the magnet. So because this is quite an efficient process, it's been possible to conduct a lot of research on hundreds of thousands of research samples. And these over the years have led to over 850 publications of NMR lipoprofile data. So it's really something sort of different than mass spec in that it's harder to generate the clinical association information that's needed prior to clinical translation from mass spec. It's easier by NMR. So we know an awful lot about the clinical value of what the NMR spectrum produces. So the intention all along actually was not to have a lab testing business, but to make these analyzers available to other laboratories. And to this end, FDA clearance was achieved for the first proprietary analyte, LDL particle number, and then the analyzer itself called Vantera. Millions of tests were performed, and several of these Vantera analyzers were actually distributed to reference labs. And so really what makes possible routine NMR testing is an instrument that looks nothing like a research NMR spectrometer. That's the whole idea. This is meant to be operated by a medical technologist with no training or knowledge about NMR whatsoever. And this, as I said, was FDA cleared. It really is successfully met the goal of being very simple to operate. There's no reagents, no consumables, so it's a very efficient and inexpensive test to perform. And you can see some of these other characteristics. The samples are introduced in the form of the original blood drawing tube, so there's no pre-analytical processing necessary whatsoever. The samples are withdrawn and diluted on board the instrument and flowed into the magnet, not introduced into the magnet in separate glass tubes. So that's about all the time I have to tell you about Vantera, but I do want to show you a 30-second or so video that was generated to show people at clinical chemistry meetings. So there you have it. But as I said, in 2014, the company was acquired by LabCorp, and their interest was in performing these tests in-house. And so these analyzers that were in these reference labs were brought back. And the main activity since then has been devoted to developing new LDT assays and clinical applications. So I'm going to share some of those with you in the last few minutes. So it turns out that the best clinical fit for NMR, as I've sort of indicated, is for high volume routine testing as opposed to esoteric tests, primarily because you're restricted to the fairly abundant metabolites that are in plasma. But since many of these are lipid related, it's not surprising that cardiometabolic disease is the sweet spot for NMR testing. And of course, cardiometabolic disease is something that is on people's minds post-COVID. In particular, this made people particularly susceptible to adverse consequences of COVID. But it's not just cardiovascular disease, it's diabetes, it's the obesity epidemic. And so all of this is a great concern and really a reason why we really need to do a better job with prevention. So this is a good review article that describes cardiometabolic-based chronic disease and how it's driven by obesity, adiposity. So you see adiposity at the top, you see the diseases, diabetes and cardiovascular disease at the bottom. But what actually causes the diabetes and the cardiovascular disease is not the adiposity per se, it's the intervening metabolic dysfunctions. And so there's hyperglycemia associated with this and dyslipidemia. But the main drivers of the diseases are insulin resistance and inflammation. And the usual testing that gets done in a lipid panel, for example, does not include these very important contributors to cardiometabolic disease. So if one wants to do a better job with prevention, so-called precision prevention, as people have talked about, like precision medicine, what would make this possible would be a repurposed and upgraded lipid panel that would be performed instead of a regular lipid panel that just worries about dyslipidemia. So dyslipidemia and hyperglycemia already are being tested for, but insulin resistance and inflammation are not. And it just so happens that the single NMR blood scan not only gives you the dyslipidemia and the hyperglycemia, but it gives you, importantly, a good measure of insulin resistance and also inflammation. So I want to talk about those two elements now. First of all, insulin resistance, and something that I think people don't generally appreciate. is that insulin resistance is the root cause of diabetes. It causes over time progressive loss of beta cell function. So the beta cells aren't able to produce enough insulin to overcome the insulin resistance. And so that leads over time to a loss of beta cell function that translates into hyperglycemia, which is mild at first and then gets greater prediabetes and finally diabetes. And as you probably know, what is happening these days is that diabetes prevention is really focused only on people that already have hyperglycemia, prediabetes. And that's primarily because it's easy to measure glucose and it's not easy to measure insulin resistance. So rather than focusing prevention efforts on the root cause of diabetes, the focus is on essentially the effect, the hyperglycemia. And in so doing, you're really losing the opportunity to intervene early and do something about diabetes risk. So it turns out that a single NMR spectrum produces 13 metabolites that combined give you a good readout of insulin resistance. This consists of the lipoprotein insulin resistance score that has 6 lipoprotein contributors to it, branched chain amino acids. And then since we haven't published on this NMR-IR score, I'm going to not disclose what these additional 4 metabolites are. But I just want to show you that in a large population of people that had this measurement performed, if you use the NMR-IR score to divide people into deciles, and then you look in each of these 10 subgroups at the insulin resistance as measured by insulin and fasting glucose, you see that in the red bars, a gradually increasing insulin resistance associated with the higher NMR-IR score. But then you also see in the blue bars, with a 10-year follow-up period after the NMR measurement was performed, this is the rate at which future diabetes occurs in these 10 subgroups. And you can see that the NMR-IR score is definitely tracking with the prevalence of future diabetes. So this is really a quite useful biomarker. And then turning to glyc-A, the inflammation marker, I talked about its quantification earlier, but it is actually quite useful because the NMR signal is contributed to by several acute phase proteins. And so essentially how big this signal is a measure of systemic inflammation, a sort of a composite measure of inflammation. And because it's composite, it has generally stronger disease associations than CRP, which is the main inflammation biomarker that's used clinically. And it also has much lower biological variability than CRP, so it doesn't bounce around a lot from day to day. And just one quick example of a paper published last year that directly compared glyc-A and CRP for the prediction of future myocardial infarction and stroke and other cardiovascular outcomes. This shows that for myocardial infarction in particular, that glyc-A has a stronger ability to predict these events than CRP. So what is really quite remarkable is that a single inexpensive NMR scan produces all of the information shown here on the left. It could be output in the form of a patient report that might look something like this. The metabolites that together generate the insulin resistance marker, 13 in this case, is a good way of taking metabolomic information and making it, outputting it in simple form for clinical translation. And then finally, what I haven't mentioned yet is what's at the bottom, which is this additional multi-marker called MVX, or the Metabolic Vulnerability Index. And I'm going to spend the last couple minutes telling you about this marker of mortality risk, which is really quite remarkable. This is something that's brand new. This was reported on for the first time just 2 weeks ago in a paper in the Lancet Healthy Longevity. And the interpretation paragraph of the abstract says the following, that MVX made a dominant contribution to mortality prediction in patients with both cardiovascular disease and in low-risk subgroups without pre-existing disease, suggesting that metabolic malnutrition inflammation syndromes might have a more universal role in survival than previously thought. Obviously, you need to read the paper to understand exactly what all that means. But in terms of the ability of these markers to predict future mortality, I just want to show you data from the CathGen study. So this is about 6,000 patients that came to the doctor for cardiac problems, for cardiac catheterization. And over a 5-year period of time, 1,000 of them died. And if you generate a prediction model that has these 15 parameters, including age, and you look at the relative contribution of each of these to the overall prediction of mortality, you can see that these 6 parameters here make a very substantial contribution. These are 6 parameters that come from a single NMR scan. And when you brew these together into the MVX score, you have a score that contributes about 70% of the overall prediction of the model, that includes age and all sorts of other things that one would imagine are quite important predictors of mortality, like whether the patients have heart failure or diabetes or hypertension, et cetera. So this is really quite remarkable in terms of how dominant its prediction is of mortality, something that really was not known before. And this is a good example of how remarkably well these 6,000 people in this study were differentiated just on the basis of their MVX score at baseline. You can see that the numbers in parentheses are the number of people in each of these MVX categories. So if you have an MVX score less than 35, you have only about 3% of that group have died after 5 years. If you're unfortunately in the red group, then over 60% of the people in that subgroup have died. But the remarkable thing is that for even small differences in MVX score, there's a corresponding difference in the cumulative incidence of mortality over time. So this is really quite interesting and remarkable. And the clinical implications of this, I'll leave it to have you read the paper, but are quite profound, because it suggests that survival may depend more on previously unrecognized causal factors that are related to malnutrition and inflammation than those that are thought to actually be the causes of death. So this sort of cartoon indicates that the traditional thinking is that you die from things like cardiovascular disease, cancer, and of course older age. But the intervening metabolic vulnerabilities really dictate largely whether you succumb to any of these diseases. And so by at least recognizing this and having a biomarker that does a good job differentiating people who are metabolically more resilient versus vulnerable, as it says here, treating these underlying metabolic dysfunctions might provide greater survival benefit than targeting conventional disease risk factors. So it remains to be seen how useful in the future this will be, but it's just the beginning, but it's really a quite remarkable finding. So finishing up, I just want to sort of summarize the various things that one might expect would be necessary for routine NMR testing to be broadly clinically translated. And what I'm showing is that most of these have been accomplished. There are unique NMR biomarkers that address major chronic diseases. They've been extensively published on, they're extensively validated. There's an NMR analyzer that can produce this information very efficiently and cheaply. It's been used in this way for over 10 years. Regulatory challenges have been addressed. There are a broad international patent portfolio, and these assays and the technology is available for licensing. The only thing that's been missing and continues to be missing is an IVD company to basically deliver the analyzers and metabolic assays to clinical labs worldwide. But hopefully, with all of this background and 35 years of work that's gone into proving that this is a viable proposition and could be very useful clinically, hopefully an IVD company will be motivated to bring this to patients and clinicians. So with that, I just want to quickly acknowledge the very important contributions made by the scientists, engineers, and staff at Liposcience over these many years, none of this would have been possible without their work. So with that, I will stop and wait for the discussion.
I'm back here. Sorry, couldn't find the button anymore. Thank you, Jim. Great presentation, great overview of these achievements. So I guess we can now go to the Q&A session. Anne, would you like to join us?
Hi.
Hello. So I'll start to read the first question. So this is a question that came in from Anne. For Anne, Dr. Ben, can vitamin D metabolites be measured using GCMS?
Can you hear me?
Yes.
Okay, cool. Yeah, thanks for the question. We don't do that, but I think it's possible, especially for the higher abundant vitamin D metabolites. It's probably not possible for the lowly abundant metabolites, for the 125, for example, or the 24, 25. But yeah, it should be possible. The problem with GC, of course, it takes very long. Like a GC run for vitamin D, I think it's about half an hour. So that might not be something you really wanna. That might not be very cost effective if it takes so long to actually measure it. So I guess, in short, it's possible, but it's not practical or economical.
All right, thank you. Another one for you. How do you think that different instruments and different extraction methods can influence the Ceramides panel significantly for a pathology?
So I think this probably refers to different triple quads. Or how do you understand this question? Different instruments, as in it's still different mass spec, but by mass spec by different vendors, perhaps. That's how I understand this question. I know that recently there was so I think the different extractions and the different instruments, they do not matter that much, because you always, when you quantitate the ceramides, you always add the deuterated internal standards to your sample. So the extraction is not even very complicated extraction. It's basically just a precipitation. So you take the bit of the plasma and you add precipitation solution, which is ethyl acetate with isoprop, and the internal standards to deuterate are added into that liquid, that extraction solvent, and that then is already basically just mixed and spun down and injected. So it's not a complicated extraction, even if you then have differences in the instrumentation, you can always normalize and really quantitate your signal, because you had spiked in those internal standards with a known concentration. So if you introduce an error due to different extractions or different instrumentations, you can correct for this error because you have added the deuterated internal standards.
All right.
That's how, yeah, I hope that answers it, yeah.
Thank you. So then we have a question for Jim. Is Dr. Otto suggesting that CAD future mortality might be addressed via specific nutritional intervention or research into the same?
Yes, that's what's really intriguing, is that with an understanding that there are different influences than one might expect on this metabolic vulnerability. Because this is related to inflammation and malnutrition, certainly nutritional therapy is a possibility, anti-inflammatory treatment as well. So this is really, you know, because this is brand new, these ideas all need to be followed up on. But there's, with a good biomarker to be able to lead you, I mean, what would be ideal is if one could show that a reduction in the MVX score directly translates into a reduction in mortality. And if that could be shown, then MVX could serve as a surrogate endpoint and make clinical trials for therapeutics for extending lifespan much more efficient.
Okay, thank you, Jim. Maybe another one for you that came in concerning the different diagnostic panel that you presented. Are they really valid for all patients for screening? Metabolomics being very dynamic, aren't there biases related to physiological status, to drug treatment, to gender, etc.?
So I'm not sure I understand the question. If it's related to the question of how stable are these metabolic status that you get in a readout with a single NMR scan at a single period of time. What's actually been quite interesting to find is that, at least in the absence of any kind of intervention, like a dietary intervention that causes you to lose weight, or a drug intervention, you know, the metabolic status and these biomarkers are really quite stable over time. And so this is something that people worry about, that you can't use a single readout to really inform clinical decision making. But just as cholesterol is able to do that, so are most of these markers that I talked about.
All right, thank you. We're getting many questions. I hope we can answer as many of them as possible. Otherwise, we'll try to follow up by email. I'm taking now the next one. It's gone. Anne, did you look into details how to calculate SER2 score from concentration of ceramides and PCs? Is it based on quartile concentration levels of each lipid, or on more complex calculation by Cox regression?
Yeah, so actually, I just looked that up. So I just take the liberty of reading it from the publication. It's a combination of taking individual concentrations of some molecular species and also calculating the ratio of some of them. And then it's based on quartiles. Yeah. So for the SER2, it consists of 1 ceramide to ceramide ratio, also of 2 ceramide to phosphatidylcholine ratios, and then a single phosphatidylcholine concentration. So those three. The 3 different ratios and 1 concentration. And then, based on quartiles, it's a point system that's basically accumulated. I can send you the publication, David, if you're interested in this. Thank you. I hope that answers the question.
Another question for Jim. Some glycobiology biomolecules like pyruvate lactates are easily degraded. Can they be measured by NMR spectroscopy technique?
Well, certainly pyruvate and lactate are actually easily measured by NMR, and they're part of what comes from a single measurement. So the answer is yes.
So that's
Eli, there's a question on the commercial standards for the ceramides.
Oh, go ahead, please.
Yeah, so there are. It's true. I mean, in total, there are dozens of different ceramide molecular species available, and commercially available is a mixture of just some of these. So basically, those 4 molecular species that are used for the third assay, those exist as a deuterated form, and that one is commercially available. So that's typically what's been used to then
Okay.
Basically, you use those that are commercially available. Yeah.
Okay.
Or you hire a chemist and he synthesizes that then for yourself. So some lipid researchers started to just hire a chemist and then they would synthesize, because it's a big problem that internal standards are not commercially available for everything we need. It's actually quite a big problem. Yeah.
Okay. Another interesting one probably for Jim. What's your view on this, Jim? What will it take for NMR to be taken up by IVDs companies? What are the cost implications of adopting NMR?
Well, so that's a commercial question, and the thing I wanted to try to get across is that normally people think that in order to have something adopted for clinical use, the main hurdle is finding out if it's useful, and then the delivery is actually takes care of itself, the commercial delivery. In this case, because NMR spectroscopy is not something that has been normally found in a clinical laboratory environment, it's considered quite foreign and exotic. And what we really tried to do at Liposcience was show that that this is a very useful modality and very practical, and there is no technologic barrier to making NMR a routine part of clinical diagnostics. So it's really more a matter of whether IVD companies have thought about this. Liposcience had a business model that was economically feasible, I will say, and it was an IVD company. So it's just waiting for another IVD company to take on where Liposcience left off.
Okay, then question for Anne again. I'm looking for the one with the reference intervals. Anne, if you see it, help me.
Oh, yeah. I mentioned that there are no reference intervals for lipidomics available yet. Are there any barriers to obtaining these? And what I meant with that is that, of course, we have reference intervals for those lipids that are already routinely used for diagnostics. So, for example, reference intervals, of course, exist for triglycerides and I guess also for bile acids. But they start to be available for these emerging ceramides. But for those lipids that are part of a lipidomics panel, but they're not used yet for routine diagnostics, no one has established the reference values because so far there's no clinical utility for running lipidomics panels, so no one yet went through the work of establishing reference values, reference intervals for all of these hundreds of lipid metabolites. And one barrier, I think might also be that these methods are not harmonized or even standardized. So I think it's more powerful. The way I understand how the community comes up with reference intervals is if you measure the concentrations in various populations worldwide and that you use harmonized or standardized methods for that. And we don't have that yet for lipidomics. That's the biggest barrier.
Okay, thank you very much. So we're coming at the end of our webinar. I have a couple of announcements. So first of all, thank you all for attending this webinar. We had over 3,000 people that registered for today. Thank you, Anne. Thank you, Jim, for your great presentations. And then, of course, we'd like to thank Dr. Hamilton and Smeralda for providing the technical support for this webinar, as well as to the IFCC for offering this tool for their e-learning. So we will try to answer all the questions by email after this webinar. A certificate of participation will be provided at the end of the webinar after a few questions. So just stay in the call, you will get a few questions, and then at the end at the end of the page, you can go and show my scores and get the certificate at the bottom of the page. And last, the on-demand content of this webinar will be available in short, and you'll be informed via email. So there will be soon other IFCC webinars. Also, the IFCC Metabolomics Working Group is preparing another webinar, hopefully for October or November. And this will be announced via IFCC communication channel, email, website, and IFCC social media. So thank you all, and goodbye. Have a good day.